is s plus 3 over 2 times s plus 1. So again, in the limit, we get the 1 over 2, but only in the limit where the integration is of high enough order. And then our analysis has another caveat that the level set of the Lyapunov function now also matters. So this is for the strongly convex case. Monzer, here's the Lyapunov function. And it's this, the choice of the scaling actually matters. And so the analogous result is here that if you use, let's say, an integration of order 2, you get L over mu over to the power 5 over 6. So better than gradient descent, but not quite square root. As you increase the order of integration, you do this. Now, like I said, there's this trick here where you have to take the maximum of the level set in here. We haven't, this probably means our Lyapunov function is still, even though we can prove acceleration, it's still in a large set, but it's still not global. And so that means there's a room for improvement. So this is just some simulations, but let me just talk about what we're trying to do. So one is what I just said, which is for non-convex problems, if you assume boundedness, can you actually do better? Can you get a bound if you show that the higher order derivative? The most important thing is what Sanjoy said. What can we say in the stochastic setting? So Mert Gurbuz-Balaban, who was a postdoc at Leeds with Asu, he has a recent result which proves acceleration for the stochastic set, but only in the quadratic case. Not then the analysis is here. And what we're trying to do is, what would be the analog of going from the continuous SDE and discretize the continuous SDE to get a stochastic gradient type? No, I'm saying in the stochastic setting. Yes, but the problem is I'm not going to get rates. That's the whole point is, can I actually prove I mean, it's not convergence. We already know. Everybody knows that. The question is, in practice, everybody who uses stochastic gradient descent for these big machines, they add a momentum term and it seems to work. But there's no proof that actually, so that's something we'd like to do. Another thing, yes, exactly. Yes. Exactly. So you're trying to do that. The other thing that is kind of interesting is, again, from a control theoretic point of view, is that once you do add this momentum term, when you look at the dynamics, you make the dynamics non-normal. What do I mean by that? That it's basically the A matrix no longer commutes with its adjoint. And we know from control, Monzer can tell you, that if you take non-normal linear systems and you add noise, you actually amplify noise, even though the dynamics would be mean squared stable, but you can actually amplify. So there might be a trade-off between how much acceleration you get and how much noise you actually amplify. So that trade-off is actually not very well understood. Yes? So I think so I think the people have already shown that that projection can get there for our special, but I don't think that's sort of a slightly, it's not an irresponsible guess, but it's still a guess that that it's probably will go through. And okay, so let me just stop here and thank you for your attention. Thank you. Yes. Nesterov is not a discretization. We don't know. That's the thing. That's precisely the question. It's not a discretization. The only change that it has Nesterov has is that it evaluates the gradient at some midpoint, not at. Yes. No. So the answer. So that's where we wanted. That's what we wanted to discover. And in doing that, we discovered an alternative path for getting acceleration, but not the Nesterov. So that question is still open. No, we don't know. And to my knowledge, there is no. I don't think there is one. There is. Yes. Well, always something happens. Sure. Of course, yes. Yes, true. Okay. Yes. Well, it's about adding an integrator, but yeah. Yes. Yeah, so in fact, another way to say it is Nesterov is a PID control. Yes, yes. So yes, that's the. But in the end, you want a basis to guess the Lyapunov function that proves. No, it does actually come. Right, but that's as a right. Right, but it's this. Well, it's actually the scaling that matters. Yes, yes. So that was precisely what my hope was, which is, and that's why people have invested some time in this IQC machinery to figure out. And the problem with that is, if you know what is the rate that you're trying to prove, you can, yes, but you can't get, and you can't get a symbolic argument. This is the problem. You can't solve the KYP lemma symbolically. Well, so what I'm saying, first of all, the point of the approach, I guess, was to say that the intuition that you don't need the integration to preserve the mechanical properties. That was really the message. The first message was that any integration so it's not the symplecticity, but it's the order. And then that's one message. The second message is that the Lyapunov function has to be refined, and that's something that I didn't show from the continuous side. But you may be right that it's not. If we want an algorithm, maybe, I mean, this is how Polyak did it. But just because Polyak did it that way does not mean that we have to do it that way. But then the other thing is, okay, so in the continuous time, we can show the rate. Now, of course, we know that by rescaling time, we can do anything. We can extend the rate any further. But a lot of the tools that we have for nonlinear control are not well suited to get rates, because a lot of the proofs for these, non-kinematic, dynamic, second-order things, they rely on LaSalle. And LaSalle is a topological argument. It never gives you a rate. Yes. So exactly. Yes. So in fact, going along that line, and one reason that you might be, there might be worthwhile going to the continuous world, is that in continuous time, Eiserman's conjecture is true for second order dynamics. In discrete time, is false for second order. In continuous time, to get false, you need third order dynamics. It's because of the phase in the night. Yeah. So that might be a reason to stick to, because you see, the Runge-Kutta machinery shows that we can do a faithful discretization of a continuous dynamical system in a way that preserves the rate, right? The problem was that the robust control way of sector bounding the nonlinear, and in fact, I don't know if this is true or not. So I know that Eiserman's conjecture is true for continuous quadratics, but we don't know whether it gives you a rate that is the same as for lines. So let me make the statement precise. Suppose I have this dynamics x double dot plus mu x dot plus this sector bounded nonlinearity, right? The nonlinearity is monotone increasing bounded in two sectors. Is it true that the rate for any monotone increasing nonlinearity would be the rate of the worst linear thing in that sector? Right? So it's not, I don't know it. Exactly. But we know that for stability it's true. So no, it's finite time. That's the thing. So I want to get epsilon close. How many steps do I need to get epsilon close? I want to be able to, without using Hessian information, right, use something else. And in some ways I'm cheating, because instead of using Hessian at one point, I'm using gradient at many points. Yes. Yes. Right. If I have all the infinite, and if the function is analytic, I have all the terms. Right. So I know in the limit the continuous and discrete, but I don't know the rate. And people who do geometric mechanics and discretization, yeah, I can write it as a degree of stability problem, and I solve it as an LMI, but I can't get a proof. Yes. Yes. Thank you so much.